the slides, just a few quick announcements. If you didn't see the post on Piazza or the Autolab stuff, the learning objective for program execution it's posted on Autolab. You have some form of feedback. If you got the objective, the feedback usually isn't too meaningful. It's just good job sometimes. But if you didn't get the learning objective, there's feedback saying what you can do to remedy that. So check Autolab, click on your score. Whether you completed it or not, click on the score, and you'll have the feedback results there. I spent all of Saturday reviewing those, so whatever feedback you have, that's me coming directly from me saying this is what you can do. There's a Piazza post. I'll miss some details. Check the post. Make sure you get the appropriate information. For a lot of you, you just got to finish up some lecture questions, and you'll be able to finish that. Once you get the lecture questions in, the next time I do learning objective checks, I'll see that and then be able to mark you off. If that is the case, you just have lecture questions to do, and you don't do those lecture questions, you can still get the learning objective on future questions. So if there's one you're really stuck on, you just don't know what's going on with that lecture question, you banged your head against it, and you know you understand the concept, but just something about the question itself isn't gelling with you so well. There will be other opportunities. There will be other lecture questions that test the same content. So you will have more opportunities than just what I gave you. What I give in that feedback is just your immediate, like, this is what you can do right now if you want to get this done and over with and off your plate. Some of you didn't get the third bullet point, the one that I was only able to test in labs, that there's no real lecture question I can write to make sure, to see if you understand where stack and heap memory, how that's allocated and how that works throughout program execution. So if you got that, there will be a few more lab activities that also relate to the stack and heap. Specifically, the third learning objective, when we talk about immutability, and you know how for now I've been saying strings, we can just pretend they go on the stack. Well, we're going to fix that. We're going to show what happens with strings and what it means for a string to be immutable, and talk about that, how it relates to the stack and heap. Also, for the fourth learning objective, when we talk about linked lists and trees, we're going to talk about the heap and references, and all those topics are going to come flooding back. We're going to really look at how a linked list works by having separate nodes with values on the heap, which refer to other nodes that are also stored on the heap somewhere else in memory. Same with trees. So all that's going to come back. You'll have more opportunities to get that third bullet point on those future labs. So there will be more opportunities. I don't want to see anyone giving up on the class because they think, oh, I have a 0 for this learning objective, therefore it's an F according to the syllabus. It's not true. You will have more opportunities. And of course, the last ditch, the last chance, the final exam. You can always show up on the final exam with no learning objectives, and it'll be very, very difficult to do, but you could potentially verify all 15 bullet points on the final exam and get that taken care of. If you're in that situation, I wish you the best of luck, but if you weren't able to get any of them throughout the whole course, I don't see that happening. Don't rely on that. I don't see that happening. But in theory, that is possible. So maybe you know all your stuff, but something happened where you just couldn't submit. I don't know. I don't know what situation that could be. The other thing I want to talk about is the homework. We just had the first homework deadline, and I haven't been very clear about how the application objectives go. I've been focusing mostly on the learning objectives since that's where I take the hard stand, all or nothing, complete all 5. So I wanted to make sure everybody was clear on that, so nobody was thinking that I missed a lecture question, therefore I failed the class. I don't want any misconceptions like that. So I haven't been talking about the application objectives much, so I want to talk about that a little bit. If you didn't finish the primary objective for these homeworks, that does not mean that you won't get the application objective. So I want to clear that one up first of all. If you put some effort into these homeworks, into one of these homework assignments, and I can see that you have some effort. You went to the verification lab this week and you have some good thoughts. There's something there, even if you didn't make it very far on the homework assignment itself. You'll get some form of feedback similar to the learning objectives where I'll say, here's what you can do to remedy this situation. Here's what you can do to make up this application objective. When I say a hard deadline for the homeworks, it's a hard deadline for that first round, if that kind of makes sense. At that deadline, that assignment kind of shuts off for that verification. And the reason I do that, one of the major reasons I do that is because the verification lab, everybody has lab at different times, different days of the week. There's a big difference between Monday and Friday. I can't just say you have until your lab to do the homework. It's just not fair for those Monday lab students. So there's a shut-off in that for that submission of the code. Go to the lab, do the verification lab, and then after all the labs, hopefully I'll get to it again Friday or Saturday this week, you'll get that feedback similar to the learning objectives of here's how you did on the homework, either good job, you got the application objective complete, or you didn't get the application objective, here's what you can do to remedy that. The only time somebody's going to get just a flat 0 is if, 1, you didn't make any submissions to the homework, that's easy. 0, you missed that opportunity, you're no longer playing for an A at that point. If you made some submission, but it's just absolute garbage, maybe you didn't make it even past objective 1, you went to the verification lab and just had absolutely nothing, those two might just get thrown into the, okay, you missed this one, you didn't do anything before the hard deadline, you're done, you're off the stream. Anything in between, you'll get some form of feedback that says, hey, looks like you struggled with that, let's see what we can do. I don't exactly know what the feedback is going to look like. It'll be different depending on each situation, but there will be something, some way you can remedy that. And that's why if you notice the homework deadlines, I say it's a hard deadline, but you can still submit until May 8th. That's part of this, part of the having more rounds of being able to work on these things. It's not just one and done for the application objectives. I haven't been clear about that, I haven't been vocal about that at all, so I want to make sure I get that out there. I wish I would have before the deadline, I know, but just getting that out there. And just, I suppose I'll give a heads up on this. If you put some effort into the homework assignment and just didn't get anywhere on it, but it was enough for me to say, okay, you did put effort, you're not out of the running for this. One of the pieces of feedback I'll give, one of the options I'll give for students like that is, well, you had a choice of 2 homeworks, you tried this one and didn't get it before the deadline, do the other one, and you'll be able to make up that application objective. So that will be one of the options if you just didn't make it far at all. If you made it close to the end, I might just talk about, okay, here's the part you missed. Take some more time, figure out this last part, and then be able to complete it. So with that, any questions about this stuff before we go into the state pattern? Okay, let's go into the state pattern. Okay, lecture question today, and the lecture questions all this week, all 3 of these, they're going to be related to the state pattern, lectures related to the state pattern, which means these lecture questions are going to follow the same rules as the homeworks. No control flow. So this question, Wednesday's questions, question, Friday question, no control flow allowed on these, and the grader will reject. If you use any control flow, the grader's going to reject it. You're going to see very quickly that you tried to do something you're not supposed to do. It violates the assignment. Not allowed. For this one, we want to simulate a player class, which has several different states that it can be in. Thinking about a 2D platform similar to Jumper, which the Jumper state pattern. We're going to talk about that Wednesday. Go through how all of that works. If you want to get ahead, not really get ahead, but you should at least take a look at that game if you haven't already. If you did Rhyming Dictionary, at least take a look at the Jumper handout and the code and what's going on. Get a feel for what that even is, so you can follow Wednesday's lecture a little better. For this one, a player that can do 2, how do I want to word that? Can do 2 different things. We can get the jump height and movement speed out of this. And the player is going to have different jump height and movement speed based on their current state, whether they're ducking, standing, or running, and methods that can transition between those states. And just a warning this week, I'm going to say the word state so much it's going to lose meaning, but we'll get there. I have one slide where I say state like 5 times today. So we have these 5 methods. How do we implement this functionality where jump height and movement speed have different output based on previous method calls without actually, without having any control flow? So we would like to say if, have like Boolean variables for ducking, standing still, running, and say if ducking 4, else if standing 3, else 6. We'd like to do something like that. That would be the natural thing that we would normally do. How do we do this without control flow? That's what we want to be able to get to today. So let's talk about how to do that. So the state pattern, this is what we call a design pattern. There are a lot of design patterns in programming. We're only going to focus on the state pattern for this course, but if you want to look up more design patterns, the Gang of 4, they kind of put out the original design patterns. If you search them, you'll get all kinds of design patterns, or just searching design patterns directly, you get all kinds of different patterns, all kinds of different things people do with OOP to be able to kind of solve common situations that we have in programming. So if you want to do deeper diving, there's plenty of information out there, but for this class, we'll just focus on the state pattern. And specifically, before I get these questions, the state pattern, it's not like this is what you do, and some students get this misconception that control flow is bad, that's why my professor's banning it. None of that's true. This is just an application of OOP. Really what I need you to understand is inheritance and polymorphism. The state pattern is another application of those 2 topics, which really drives home these points of what we can do with inheritance and polymorphism. It's not that control flow is bad, but if I ban control flow, I force you to use OOP. Just like when we talk about functional programming, I'm going to do things to force you to use functional programming. OOP and functional programming, they're 2 different approaches that you can take to developing software. Neither one is necessarily better than the other, but I'm going to restrict certain aspects to force you to use the approach that we're learning in the class. So just before I get those comments, it's not that control flow is bad. That's not true. But if I take away control flow, I'm forcing you to use object-oriented programming. So the state pattern, application of polymorphism and inheritance, of course. Instead of changing an object's behavior based on its state variables and the values of those variables, we would like to use the state pattern to change the behavior of an object based on the type of one of its state variables. So if we want some change in behavior, we would use, if we want some change in behavior, we'll typically use conditionals, we'll use control flow. We'll say if my state variables are in this certain state, have some behavior, else have some other behavior. And sometimes we want completely, significantly different behavior in our objects. So a lot of times, the conditional behavior is going to be like if the players, not necessarily if, but throw this ball based on the player's strength, for example. So the ball's velocity is some function of the player's strength and maybe the mass of the ball, or we just have equations that are going to determine what the behavior should be for that specific application. But what happens when we want to significantly change the behavior? What if we have something that's going to not just be some function of the variables, but just completely different behavior depending on a variable? At this point, we would use some conditional, say if we're in some certain state, we'll have this behavior. Otherwise, we'll have completely different behavior. And this works, this is fine, there's nothing wrong with this. But what happens when we have a lot of different behaviors that we want to have? Every time we want to add a different type of behavior based on the current values of the state variables, we're going to have another else if block in this big chain. Again, maybe this is okay depending on the application, but this can get difficult to maintain. What if each one of these behaviors is completely different? And we have this huge block of code with a ton of complexity that we have to run and maintain and add to when we add more behavior. How are we going to test this specifically? To test one function or one method that has significantly different behavior depending on the state, your test suite is going to be massive for that. You're going to have a huge test suite to test, make sure that you're hitting every conditional in this, every block in the conditional. And if your tests fail, you got to do some digging to figure out which specific piece of functionality failed in this huge block, this huge mess of code. So this can be difficult and hard to read. If you have a newcomer onto the team and they're looking at this, it's going to be a little tough for them just to get up to speed, just to figure out how your project is organized. So let's do something new. Let's try the state pattern. Let's pull this thing in. And instead of making decisions on behavior based on values of variables, where we're saying if this Boolean expression resolves to true, do this, else if this Boolean expression resolves to true, do this, instead we're going to defer to types to be able to change behavior. So now we're going to store an object in a state variable, and that object is going to have different functionality based on its type using polymorphism. So we're going to end up with a lot more, what I call pieces of functionality here, but methods and classes. You're going to have a lot more methods and classes, but each one's going to be smaller. They're going to be a lot easier to test. You're going to have one method that does a very focused, small piece of functionality, easy to test, and then test each one of these individual methods. And then if a test fails, you know exactly where to look. This test failed, it's exactly in this method, which has maybe 5 to 10 lines of code or something. It's a lot easier to test, maintain, bring new people onto the team, etc. So how we're going to do this is write an abstract class that's going to represent our state. And we're going to store a variable of this, an object of this type, of this state type, in our class, and we're going to defer all of our functionality to the state object. That state object, we're going to code to the abstract class, and then we're going to have the functionality be determined by the actual concrete class and its overridden methods. That's what's actually going to happen when that variable is accessed, when we tell it to do something. This state variable is going to define what we call an API, an application programming interface. For our purposes, a list of methods that are the methods that the state is in charge of. So the state abstract class defines all the methods. Okay, here are all the methods that the state is responsible for. And then any concrete state that we can be in has to implement all of these methods. And then the object that we're concerned with is going to defer to the state whenever it needs to call one of those methods. All right. So what are we actually talking about here? So let's see an example and see how we would actually do this in code and what we want to accomplish here. So meet Bruce Banner if you haven't already. If you're not a Marvel fan, you might not have met this guy yet. But Bruce Banner, he's a world-class scientist, very brilliant guy. He's able to drive a car, which we'll see why that's important in a second. But he's not very good in a fight. He doesn't really have your back too much in a fight. However, he can transform into the Incredible Hulk. Hulk cannot drive a car, he just smashes the crap out of him. He's excellent in a fight, but he doesn't have very much control. So we have one person with two vastly different behaviors depending on his current state. So how would we represent something like this in our programs? How do we represent an object of type Bruce Banner and have him be able to be in these two different states? Again, without just having a big conditional. If he's currently the Hulk, do this, else do this. So we want to simulate this. Bruce Banner, who can successfully use a car, but isn't good in a fight. And the Hulk, who cannot use a car, but is great in a fight. So let's create our Bruce Banner class. I suppose it could be an object. There's only going to be one of him. And he's going to have some state variable coded to an abstract class that's going to define the methods that we can call, that we can defer to the state for, and initialize this to a Dr. Banner state class. And we'll see those classes defined on the next slide. And we're going to define 3 methods that we can call on Bruce. We can either make him angry, calm him down, use a car, or fight. So the 2 behaviors that we're concerned with, how does he currently react to cars, and how is he in a fight? So we'll define this state class, which is going to declare those methods that we can call. And Bruce, he's just going to defer to the state. So the state is going to have all these methods. We say Bruce Banner, make angry, we just defer to the state. Calm down, defer to the state. Use a car, defer to the state. Fight, defer to the state. So the Bruce Banner class doesn't have any functionality anymore. We're just deferring to his current state to be able to figure out how he's going to behave at this moment for each of these methods. So the state abstract class is going to define those 4 methods, saying no matter what state he's currently in, that state has to react to these 4 things. We have to have some return values for these 4 methods. And also, we're going to store a reference to the class to which the state is currently attached. So this state is going to be for an instance of Bruce Banner. So we want a reference to Bruce Banner so we can access his state variables, including the state itself, so we can change the state, which we'll talk about in a few slides here. So the state defines what has to be implemented, and then we have concrete states that are going to extend that and define the behavior just for that particular state. So when Bruce is Dr. Banner, we'll talk about these 2 in a few slides. But if you try to calm Bruce Banner down, he's already calm, nothing happens. If you try to use a car, I didn't show the car class here, but I have drive, which takes a Boolean to say whether it's overloaded or not, whether you're going to harm the suspension. I'm going to say false here. Bruce Banner's not going to harm that car. He's not overloaded. But he can drive it. So if you use a car, he's going to drive that car. In fight, well, he's not going to do so good in a fight. Of course, we're just simulating functionality by printing to the screen just to keep the code shorter here. But this is where we would have whatever behavior we need. The Hulk, if you make him angry, he's already angry. Again, we'll skip calm down for now. If you use a car, he's just going to smash it. And fight, he's going to do pretty good. He's going to hold his own. So we have these 8 smaller methods that are very specific. Instead of writing the Bruce Banner class and saying, how does Bruce Banner use a car? Well, it depends if he's the Hulk or if he's Dr. Banner currently. Instead of that, in conditionals and then different behaviors, instead of that, we're looking at a more refined way of thinking, a more narrowed down piece of implementation. How does the Hulk use a car? We just write, when he's currently the Hulk, how does he use a car, and implement that method, and then test that method. Then we have a test. How does Hulk use a car? Create a state, the Hulk, call use car, test that behavior. Much simpler to implement and test each individual method rather than trying to hit every path of your conditionals. So now Bruce can just defer to the state. We store the variable we store the state in a variable of type state. So we're only concerned with the abstract class. The state could be any of the inheriting classes. We'll initialize him to Dr. Banner. And we have to be aware of how our references are moving around. This is why we did so much reference talk. I mean, you got to know references anyway. But this is one area where we need to understand our references to be able to be successful with this. When we create a new state class, we're going to give it in its constructor a reference to the object to which the state is attached. The state has to have this reference at some point. And just a side note, if you're looking at the documentation, I linked to the Wikipedia article on state pattern. They do this a little different. The state, each time you call a method, it takes a reference. I moved that to just take it in the constructor. A little bit different setup, but the same effect. So I'm passing that reference in the constructor, and then the state has access to this Bruce Banner object. If we don't do this, or if somewhere in our state, maybe we say, take this banner, this Bruce Banner object, and create a new Bruce Banner object with all the same properties and everything, all the same state variables, values, and everything, that doesn't work. We need this actual Bruce Banner object in our states. If we're not making sure that that's passed by reference, if we have duplicates, like if we're creating new batteries in those assignments, we're not going to be attached to the correct object. In our state, in our object, think of the Hulk and Bruce Banner doing two separate things because you mixed up the references. That just breaks the whole state pattern. It breaks everything that we're trying to do here. We got to make sure the references are passed properly and not recreated. We don't want to say new Bruce Banner pretty much anywhere in this code, probably anywhere in this code, only in the code that's going to use the Bruce Banner object. So now that the state has all this behavior implemented, let's talk about these, has all the behavior implemented and has a reference to the Bruce Banner that it's attached to. Let's talk about these two lines here that we skipped over last time. So since the state has a reference to the object to which it's attached to, it has access to all its state variables. There really aren't any state variables in the Bruce Banner class except the state itself, but that's the one I want to talk about now. It has access to the state itself. So inside this class, if we have a Dr. Banner and we didn't mess up our references at any point, banner.state is actually a reference to this state object, the current state object that's being called. If I said banner.state equal this, I should get true from that. It should be the exact state that we're currently in. Those states should be the exact same reference, the exact same state. But what we can do is when you have Dr. Banner and you make them angry, we can replace this variable, the state can replace itself with a new state, which is something we call a state transition. So when Dr. Banner, you make him angry, that's going to change his state to the Hulk. Give that reference to the new state, so the new state has the same reference, so the new state knows the object to which it is attached. And now the state has successfully transitioned to the Hulk, and now these are all the methods that Bruce Banner will implement. So Bruce Banner, initially, these are the behaviors of all his methods, but as soon as you call make angry, his state is replaced and all of his behavior changes. His four methods now do completely different things. We can have drastically different changes in behavior by hitting one of these state transitions. We hit a state transition, all four methods do different things without any control flow, notably for the assignments. So we changed all the behavior, no control flow. And then if you calm down the Hulk, do the same exact thing but backwards, go back to being Dr. Banner, and he goes back to all of his default original initial behavior from that class by hitting one of these state transitions, by replacing the state variable with an object of a different type that overrides the methods of the base class, the abstract class, with different functionality. So it's quite a bit to absorb. Take a quick time out. Does anybody have questions at this point? Yes. So in the Bruce Banner class, that's where my state variable is declared. I just couldn't fit all four classes on the screen at once with my bullet points. But it's in the Bruce Banner class. We have the state variable. And this is the variable that we're replacing when we have a state transition. We have an object of type Bruce Banner, and we're going to replace its state variable named state. I told you we're going to say the word state a lot today, with a new state. Yes. we can't. So we can never instantiate an abstract class. So right here, I can't say state equals new state, but I can say state equals new some class that extends state and implements all its methods that is not abstract. So Dr. Banner, this is not an abstract class, but since it extends state, I can store it in a variable of type state. That's something we talked about last week. We can chat about that in office hours. Okay. Any other questions? Yeah, this is like when we had the dynamic object, and we had objects of type health potion, but we could store it in a variable of type dynamic object. We're doing the same thing here, but with different classes. We have state, and we extend that abstract class with 2 other classes, and we can store objects of those types in variables of the type of the abstract class. But we can never say new state. That's not allowed. We can never create a new just state class, state object itself. But we can create objects of the types that extend it and store those in variables of type state. Does that make sense? Okay. So if we call make angry, is it automatically going to call the function of the state object? Yeah. So that's what we implemented in the Bruce Banner class. So outside of these classes, outside of all this functionality we're building, somewhere elsewhere in our program, we're going to have code that says new Bruce Banner, create an object of type Bruce Banner, which probably should have just made this an object, like I said. There's only one Bruce Banner. But we're going to say Bruce Banner.makeAngry. That's going to call this method. And then the Bruce Banner object defers to the state. And it's going to say, okay, I don't know what I'm supposed to do when somebody makes me angry. I'm just going to defer to my state. And whatever my state currently is, whatever state I'm currently in, that's going to determine which behavior I have. So it's not automatic, but we wrote that code to defer to the state. Make angry, just call state make angry. Calm down, just call state.calm down. Use car, just call state.use car. Fight, just call state.fight. And this is going to be common with the state pattern. The class that actually has all of this complex behavior that's changing wildly depending on the state, that class itself usually doesn't have much functionality. For example, your calculator and microwave classes themselves won't have a whole lot of code in them. It's just going to look like this. It's just going to have all these methods, all these button press methods, and the door open, door close methods. And those methods are just going to defer to your state that you're going to create. And your state variables, that's where all the that's where all the action happens. That's where all the functionality is built. There will only be a few things, like in the calculator class, you might want state variables for the left-hand side, right-hand side, and a few bookkeeping variables. But you won't have a lot of functionality in that class itself. In the Bruce Banner class, we don't have much functionality in this class itself. We just defer to the current state, and then depending on what state we're in, we're going to have that actual behavior defined. So this is how we can change behavior without conditionals. We're just going to change behavior by changing the type of that state variable, which is going to replace all of our methods with different behavior. And we got to figure out, okay, what different states can we be in? Those are our different behaviors, and swap out those states as appropriate. Okay, but arguably, and I'd say you would win that argument, that code that we just saw would be much simpler without the state pattern. Instead of one class, we have 4, and it's a little harder to read with just these 2 states. If we just had a Boolean named Hulk in the Bruce Banner class, and then each one of those methods just said, if Hulk this, else this, we'd get away with that, and it'd probably be cleaner, better code, easier to read. Until we have really complex behavior, it wouldn't be too bad to have all of that in one class. I think you'd win that argument. The state pattern really just added more complexity. It added more files. It added more methods. Didn't really help us too much. Where this really helps, where we do get to see the power of the state pattern, is when we need to add a new state. So Bruce Banner can have this third state, Professor Hulk, spoilers, and the movie's old by now, but spoilers. Professor Hulk is a new state where Bruce Banner is in the Hulk form, but he has complete control. So he has yet a third set of very different behaviors depending on his current state. So now he can drive a car and fight, except he's going to overload the car, so we're going to set that Boolean to true. So now, to add this new state, we don't really have to do a whole lot. We don't have to reformat our code. We don't have to reorganize very much. We don't have to have a new state variable. If we have a Boolean named Hulk to say if he's in the Hulk state, well, now do we have two Booleans, or do we change that to a string? Like, how do we have this third state? We don't have to do any of that decision making now. We create a new class for Professor Hulk that extends state. And we just have to implement these 4 methods. How does Professor Hulk behave for each one of these 4 methods? This is much easier to write. We just start thinking, okay, Professor Hulk, when you make him angry, what happens? When you calm him down, what happens? When he uses a car, what happens? He can drive it, but he's going to damage the suspension. When he fights, what's going to happen? And we're very focused when we implement these methods. Well, how does Professor Hulk react to these 4 methods? And that's it. We're not reorganizing our code, restructuring everything, which could be very painful if we have it set up with conditionals. Simple. We're only worried about the new functionality. We don't even have to touch the other 3 classes that we have. Those are tested, they're done, we put them away, we don't have to do anything with them. And then we add the transition, the state transitions to this new state. And we're going to say that whether Bruce Banner is in the Dr. Banner or the Hulk state, we don't know, whichever one, he can transition into Professor Hulk by learning how to control this. So from either state, if we have the same behavior, from any state, we can put that right in our objects class itself. If we didn't, we would have to make a few changes. Say he can only do this from Dr. Banner, not Professor Hulk. We would only add this transition to Dr. Banner and not the Hulk. And we would have to change one of those classes, but only if they interact directly with the new state that we added. That's the only time we would have to modify that code. We'll put this right in the Bruce Banner class to say that he can always transform to Professor Hulk if he learns to control himself. And just have that state transition to Professor Hulk no matter what the state currently is. So we added new functionality, and it's relatively painless because we had this structure that's easy to expand. We can add more complex functionality. We can add 10 more states, and all we have to really do is implement those state classes, implement these 4 methods, and then add in the state transitions. We're not breaking existing functionality that's already been tested. When we're talking about the state patterns, it's helpful to visualize what's happening. So instead of having some mess of code that we're trying to make sense of, maybe adding comments and documentation, stuff like that, we can do those things also. But a quick visual called a state diagram is going to help us see what's happening with these. We have 3 states. We're going to represent our states as just boxes in this case, and then define these, show the state transitions. How do we transfer between each state? And specifically, what method calls are going to trigger those state transitions. So we have Dr. Banner is our initial state. If we call, and then we'll have whatever the Dr. Banner state behavior is. If we call make angry, we're going to transition to the Hulk. From the Hulk, if we call calm down, we're going to transition to Dr. Banner. And from either of these states, if somebody calls learn control, we're going to transition into Professor Hulk. And notice once he's Professor Hulk, there's no going back. He's not going to forget how to control himself and go back to the Hulk. So he's stuck in that state once he enters that Professor Hulk. We have no state transitions from Professor Hulk to the other ones. We didn't implement that in any of those 4 methods. This is a final state. Any questions on the state pattern? Okay, so some tips. on using the state pattern that we'll talk about throughout the rest of the week. So that's what the state pattern is. We'll see more examples and get more practice with this Wednesday and Friday. But here's the high level how to apply the state pattern that you use the 3 lecture questions, your homework. When you're using this state pattern, what I recommend you do to start. First, I'm going to write my API. So the API, this is in the state class, the list of methods that can be called. For the homework, it's pretty easy. For the lecture questions, today's lecture question is pretty easy because I give you the API. For the lecture question, here's the API. For calculator, for microwave, those classes already have the API. So it's creating a state variable that has all the API methods that can be called that are going to be deferred to the state for its functionality. This is anything that's going to change behavior depending on what the state currently is. So some of those methods I just looked at, they won't necessarily all be in your API. Some will always have the same behavior. So you put those in in the class that has the state. But anything that's going to change goes in your API of your state class. And then decide what states there will be. This one gets a little trickier, especially for the calculator and microwave. What states do you need? What behavior can change? Like so what behavior can be changed based on the state of the object? If you have different behavior based on the state, if there's some button on your microwave or GUI that will do different things depending on the state, you have to have a new state for that different behavior in your state diagram. You have to add a new state for that. So, and my general rule of thumb for this is if you're ever tempted to use a conditional, that's a good indicator that you have 2 different states. So for example, the decimal on the calculator, which we'll talk about when we get to Wednesday. I'll mention it specifically. But that decimal is going to have different behavior whether it's already been pressed or not. So there's a temptation, and what we would normally do if I wasn't really forcing the state pattern on you would be to say, if the decimal button has already been pressed, don't do anything else. Add a decimal point to the string of the number that I'm building, and also set that Boolean flag to true, saying that the button has already been pressed. So we're really tempted to have a conditional there, an if statement, to check that. That's the natural way that we would program this if you weren't forced to use the state pattern. So there's 2 different states there. You're in one state, and then you push the decimal button for the first time, and you're transitioning to another state. You're going to have 2 different states for that. At least 2 different states for that specific example. So what methods are we going to defer to the state for functionality? And what states do we need? What different sets of behavior do we need to get the functionality that we're going for? And then finally, determine all the transitions between those states. How do I get from one state to another? When some of these methods are called, we're going to change state. Where are all those things? So for example, hitting that decimal button triggered a state transition into some other state that's going to disable that button. Any questions? Should be the order of the classes are written. I already finished the lecture question. Yeah, thanks for bragging, but we don't need that. A book to go with the lesson. I give links in the course website. There's no real book that follows all the content that we cover in the course. Just a quick warning. I have it on the bottom of the slide on this, but just a quick two reminders I want to say. If you have any control flow in this lecture question, AutoGrader's just going to say no, it's going to reject it, and it'll give you all the compiler errors that you'll see. What I do is replace all of your control flow keywords with redacted and some asterisks. So if you see that, it means you use control flow somewhere in your code. You can't do that. This applies anywhere in your submission. So if you have one project with all of your code and you're submitting that whole thing, you're not going to be able to get credit for these because it's going to see control flow in your other classes that you wrote for other questions That's not going to work for you. And the second thing you can use, you can obviously add more packages and more classes, anything you need to be able to complete this question. I recommend having a package for your states and then putting all your state classes in there. But you will need a lot more classes to complete this one to use the state pattern effectively. With that, yeah, I got nothing. I'll see y'all Wednesday.